Okay, welcome to today's 1W-MINDS seminar. Our speaker today is Gerlind Plonka from the University of Göttingen. Just a very short CV of hers. So she got her PhD in 1993 at the University of Rostock, where she also stayed after that as a postdoc, and received sort of, I would say, the most important early career award in Germany, the Heinz Meyer-Leibniz Prize, for her outstanding work, before being appointed as an associate professor at the University of Duisburg at the time, which later sort of merged with Essen, I think. And now she has moved to the already also some 10 years ago or more to the University of Göttingen, where she now has a full professorship for signal and image analysis. So we're very much looking forward to her talk on recovery of sparse signals from their Fourier coefficients.
Okay, thank you, Felix. Thank you for the invitation and thank you for the introduction. And the topic of my talk is recovery of sparse signals from Fourier coefficients, as you see it here already. And now it's unfortunately not working. Oh, now it works. Okay, so this is work in collaboration with my postdoc Nadia Derevianko and with my PhD student Markus Petz. And you see here already the outline of my talk. So first, I'd like to give you an idea what kind of non-harmonic signals we would like to recover. And for that purpose, we first also have to look at the uniqueness of the model. That is important in this case. We will see that the non-harmonic signals are in fact like exponential sums, but a little bit different, and therefore we need to look at the uniqueness. And then we will do something else compared to what we always do. So we do not Prony's method, but a completely new method that is working with or using the rational structure of the Fourier coefficients. And this rational structure will lead us to the problem of a rational interpolation problem, and that will be solved by the so-called AAA algorithm. So I would like to introduce that algorithm. We need to modify it a little bit. AAA stands for Adaptive Antolas Anderson algorithm, and that is an algorithm which has been introduced quite recently by Nakatsukasa, CT and Trefessen in 2018. And I'd like to show you how this is working in our case and how we get then the new recovery algorithm based on this rational interpolation. And we will also see that it's really different from the usual ideas of Prony's method. And of course, in the end, if I have enough time, then I'd like to give you a glimpse that how we can put that together maybe. So we start with a very simple example here with a signal f of t, which has only two terms. Yeah, this two terms with this cosine 2 pi square root of 2t and cosines of 2 pi square root of 3t. So, and well, we are all familiar with Fourier analysis, and it looks very simple at the first glance. At the second glance, we see that this signal is not periodic. You will not find any period p larger than 0 such that we can say, okay, on an interval of that length p, we can write and find this in the simple way, because an integer multiple of square root of 2 is never equal to an integer multiple of square root of 3. So if you try to get a Fourier decomposition with a classical Fourier series, then you always come up with an infinite sum. So this is, you cannot have it differently. And I have written it here just for 0, 1. If you take a different p, it will be also an infinite sum. But if we look now a little bit closer to the Fourier coefficients, then we see that this Fourier coefficients have already a very special structure. So Cn of f, so this long Fourier coefficient here is just my Cn of f, the nth Fourier coefficient, and the n comes in obviously in the denominator here as an n squared, and here too, and then little n comes in also here in the numerator here for the imaginary part, and also here, and that's it. Yeah, everything else is just given more or less already by the parameter square root of 2 and square root of 3 that we have here. And the question is, can we use that anyhow in order to recover such simple signals from only a very small number of Fourier coefficients? So this is what we want to look at. And we of course consider a little bit more general models here, not just these two-term models that we had just in the example. We will look at real signals f of t of that type here with a certain number of terms m. M is already my first parameter that usually is not known in advance. Gamma j, real values which are non-zero, otherwise you can take that away. Yeah, so then we do not have that term. Then we have the frequencies aj here, which can be real, and the bj, which are usually in the interval 0 to pi. Yeah, that makes sense because cosine is a 2 pi periodic function. In fact, I can even simplify a bit. I can also say, okay, I take aj only larger than or equal to 0, because you know that cosine is an even function. So that means that if I put a minus aj, then I get more or less the same. If I modify a little bit the bj, so then I get just the same. So I get nothing new if I have a negative frequency. So therefore I assume that aj is larger than or equal to 0, and I need to have them pairwise distinct. Yeah, we will see that also if we think about uniqueness. This is this signal structure that we want to look most of the time in this talk, but we can also generalize it to so-called extended exponential sums. And this is really complex now with some frequencies lambda j that we have here, and which can be complex just in C. And here we have even polynomial coefficients with a certain degree nj. And it's of course clear that this real signal that we started with here is a special case of the second part here. But sometimes it makes sense to look at such special case separately, because then the algorithms get simpler, and that happens here too, and therefore I will do that. It starts already with a number of terms. So if I rewrite such a cosine sum as an exponential sum, then I double here the number of terms. Yeah? Then we get just a larger problem. So, and the question is that we want to look at how to reconstruct such signals from a finite number of its Fourier coefficients, CNF. And I'd like to mention that there are, of course, a lot of other solution strategies for recovering such exponential sums or such cosine signals. And first I have to mention Prony's method. We did ourselves a lot in that direction. So everything that is in the direction of FRI, so finite rate of innovation signals, is of course also related to Prony's method. And I could I think a full page with names with just really on the mathematics of Prony's method, and then another page for application. So there are really a lot of people who did something in this direction within the last years. If we think about more numerically stable variants, so the classical Prony method is known to be not very stable. If we look at a little bit better variants, then I have to mention music, Esprit, matrix pencil method, and so on. And the idea that we looked at such exponential sums, at least some special exponential sums, come up also if you look, for example, at discrete measures. If you have just a stream of Diracs. This is also what happens in FRI signals, a stream of Diracs. If you look at the Fourier transform of that, then you also come up with an exponential sum. And it can also be solved via convex programming algorithms. And I'd like to mention at least name Fernandez-Granda. There are a few papers around in that direction, but many more people who are interested in such an approach. And I'd like to mention two further ideas which are completely away from Prony's method, namely the EMD method, empirical mode decomposition, where one is looking at models of that type here. F of t is a sum of certain number of terms with so-called envelope function gamma j of t, and then cosine, and here we have phi j of t, which are instantaneous frequency functions. And there are again a lot of papers in that direction, especially in practice. Sometimes these corresponding algorithms are also called Hilbert-Wang transform. And there are also some mathematical backgrounds given by Debussy and by Chui, different ideas here. And what we did, I go back just here, what we did here, if I look at such a signal, then you can see this again also as a special case, of course, of the EMD structure. But what we are able to show is that our model will be really unique. Each parameter is uniquely defined, and that means that we can use this parameter and can interpret that parameter. This here, what we have here in this structure, which we have usually in empirical mode decomposition, is not unique. So this is really a drawback of such a very general model. And I'd like to mention a rational approximation paper that I have just seen that is only a few days old, came up now on arXiv in May, where also rational approximation and Prony's method is related. So, but now we start with our signal of that type here. We have our sum with m terms, and we first want to look at uniqueness, as I told you already. And we had seen already that it makes sense to take the frequencies a, j, just to be larger than or equal to 0. I would like to take out for this moment the 0. We will see in a moment why. And I would like bj we had already in this, in the interval 0 to pi, as we had seen, that makes sense. And gamma j should be also just positive in order to make the model unique. The reason is, since we can really have the bj in 0 to pi, we can here play with this cosine. It can be positive or negative, therefore it's enough to have it this way. Yeah, we do not lose anything, but we can prove now, if we take this intervals for our parameters, that the representation of the function that we have now is unique. So any parameter starting with m, then gamma j, bj, and also the a j, which should be all, of course, also pairwise distinct, are then uniquely defined by, for example, by function values f of t, if we know the signal on a certain interval of positive length. So this is important. In a more simple case of exponential sums with just constant coefficients, it is obviously simpler to see that it is true, but in our case, we needed to think about that. Okay, and now, knowing now that we have a unique model, so everything can be recovered uniquely, we want to do that with the Fourier coefficients. And if we want to do that with Fourier coefficients, then we need to understand how they look like. So here is my signal, again, the signal model. I take just one term, fj of it. This is just for one fixed j. And we take a certain p, which is the length of our period, and we would like to look at our function fj on the interval 0p, and will expand it into a Fourier series this way, as usual. Yeah, this is a classical Fourier series, and we will know in advance. So even if the function fj is, of course, very smooth, this Fourier coefficients will not decay very quickly, because we introduce an discontinuity at the border of the interval, because this is not usually not periodic. So, and the Fourier coefficients are given this way as usual, and we can see here already how they look like. So the real part, CNF, is of this type. So it's just a computation. It's not really difficult to get that. Interesting for us is that we have just the n squared here once in the denominator. Here the same for the real and the imaginary part, as you see here. And we have the n once more here in the imaginary part here as a factor. This is all. These are the only positions where the n comes in. Yeah, everything else is just depending on the parameters that we want to find in the end. So gamma, j, aj, and bj. Well, something else I have to say here, of course, this is, we need to think about for a moment, what happens if, or can it happen that this denominator that we have here is 0? And of course it can happen, namely if aj times p is equal to n. Yeah, if we take n to be here, assume that we are on the positive side, just as in positive integers, it can happen. But if aj times p is equal to an integer, then at the same times, here we have aj times p times pi is an integer times pi. So that means the sign is again a 0. Yes, this is again a 0. Then we have something like 0 over 0. And then we can apply a rule of L'Hopital to see that everything is well defined. But in that special case, of course, we will not get this nice fractional structure that we have here. So this is, interestingly, the bad case here. In our case, the periodic case will be something that we have to look at separately, which is a bit nasty here. But, and that is the reason why I'm putting now here this condition. I assume for this moment that we have here a term fj where we have a non-periodic frequency. So that means that aj times p is not an integer. So then we surely have the fractional structure. And as we have seen just before, we can rewrite that a little bit simpler. The real part of CNFJ is just of that type here. And the imaginary part is bjn over n squared minus cj, where these coefficients aj, bj, and cj can be just found from the representation that I had before. Cj is especially simple. What we had here in the denominator, that was aj squared times p squared, and so on. The aj and the bj are clear. Okay, so, and if I have just aj, bj, and cj, then it's of course a good question to ask, is it enough to have these parameters instead of gamma, j, aj, and bj? So is there a bijection between these 3 parameters that I have in my model and this parameters that I have in my Fourier coefficients? And yes, that is working. I just write it here. So we can always find, obviously, aj, bj, and cj can be written with little aj, little bj, and little gamma j. And the other way around, it's working too. Here aj is this way, as we see here from that first equation, and for the other it's a little bit more difficult but possible. And everything, it's really a bijection, so it's well defined. With the bj, when one needs to play a bit, if you really do not want to use the other values, but it's working. So this is what we can keep in mind, that it's completely enough in the end to find these parameters. And now we put that together. Up to now, we have just looked at one term here. Now we take our full signal model and assume again that we have non-periodicity, and then the Fourier coefficient CNF will look like this. Yeah, and for any j, we will have always this structure of the Fourier coefficients. And we can even more simplify if we would be able to get rid of this little n that we have here in the numerator. And I just do that by changing a little bit the coefficients. So I modify the Fourier coefficients, and this Cn tilde coefficients that will come up in my talk from now on will just be of that type here. We take the real part as it is, and the imaginary part, there we divide by little n to get rid of this little n. And then Cn tilde of f is just of this form, even more simple. So we have just, we can put that together. Then we have here a complex number, the gj, and we have imaginary and the real part and imaginary part. Then and here, these are the parameters that we need to find out in the end. This is now a simple structure. This is where we can anyhow put now a rational interpolation, and we will do that as follows. So we define a rational function R of z, or more exactly Rm of z. A rational function is always a polynomial over a polynomial here, and we would like to have it in a way such that we have this fractional decomposition of that rational polynomial. So obviously, the Q of z is obtained just by taking the product of all these linear factors that we have here in the sum. Yeah, these are exactly m linear factors. So that means Q is a polynomial of degree m. And then we have P. We can find that similarly very simple, and that will be of degree m minus 1. So this rational function that I'm looking for is of type m minus 1m, and it satisfies obviously the interpolation conditions. R of n squared is equal to Cn tilde of f. Yeah, because we had found out that it is exactly this way. If we put this z to be n squared, then we have exactly this interpolation conditions. That is true for any n, for all integers n, non-zero. Of course, yeah, we have to take out, because of this division by n, we have to take out the zero coefficient, but otherwise it's always true. And here this gamma is already the index set that I assume to know. This will be a finite set, and we will see here. Here we have it again. We will always just look at parameter, at index sets which are positive integers, because we have a real function that we want to recover, and we know already in advance that the Fourier coefficients with negative index do not give new information to us. So these are just a conjugate complex of the positive indexed Fourier coefficients. So therefore, I assume this. We need just enough coefficients. So these need not to be consecutive. We need just enough Fourier coefficients, say 2m plus 1. We will see later if m is known, it's enough to have 2m even. So 2m coefficients, but if we have some more, it's better, of course, numerically. So we want to reconstruct that. This is my signal structure. So that means we want to recover m, aj, bj, gamma j, all the parameters here now from the C and F. So, and how can we do that? I put already the algorithm, which is a simple idea now. In a first step, we just compute a rational function R of z of that type, such that the numerator polynomial is 1 degree less than the denominator polynomial, and such that all interpolation conditions are satisfied for my modified Fourier coefficients that I know. As this is what I do. And then we have it, and of course we find the rational functions of smallest type that such that this is satisfied. Then I just fix m to be k, and compute the partial fraction decomposition of that rational function this way. Has to be this way, and then we are done more or less. Yeah, then we can just read out the parameters. Cj, gj has been aj plus ibj, and then we can find all parameters little aj, little bj, little gamma j from these parameters, and we are done. So that's it. So this is the full idea that we want to use. And now the details come in. So the problem is, of course, is it indeed simple to find such a rational function of that type for interpolation? So, and if you do that in a classical way, then this will be not a good idea because that is not stable numerically. But in this case, the AAA algorithm comes to our help. And here we have it, the AAA algorithm by Nakatsukasa et al. From 2018. And this is really a great algorithm. So it works really well for our, in our case. And put that again, so what do we want? We have given our Fourier coefficient CNF for a certain index Z, gamma. And we want to find a rational function P over Q such that all the interpolation conditions are satisfied. And what is the nice thing about the AAA algorithm now? So there are a few ingredients why it's working so well. And the first ingredient is it's working iteratively with an adaptive partition of the interpolation points that are taken. Iteratively means, so we start with a very small rational function. So we're of type, say 1, 1, or 0, 0 even. So we're a very small, and then in each iteration step, we get a larger type of rational function here. In the classical AAA algorithm, we get always a type J over J. So both the denominator and the numerator have the same degree. So this is a little bit different from what we need, but we need to modify only a little bit. And the second ingredient that is important for the algorithm to work is a barycentric representation. And again, also this is not completely new. That is known for rational interpolation and rational approximation, that one needs to take such a barycentric representation. Can be seen already in papers by Beirut, for example, or in the paper by Floater and Horman. And in others, Trefessen, of course, too. And this is nicely put together here in this algorithm. So what are we doing? At step J, at the iteration step J, we try to find a rational function of type Jj. And we use here an adaptive partition of my index Z gamma in such a way that Sj plus 1 has this here contains exactly just j plus 1 indices where we want to interpolate. So these are the indices of my interpolation points that I will use. And the gamma j plus 1 is just the remaining index set, yeah, which we didn't use up to now. And then in the barycentric representation, we put in already this interpolation values that come from this set here. And they are given here. So this CL tilde of F are put in just here already. And we take the sum exactly over that index set. And doing that, so this is the special barycentric representation where you see that already, I call that P tilde and Q tilde now because they are themselves now again rational functions, but you can simply see that it is also a rational function together, since we can of course expand by these linear factors that come up here and there, both in both denominators, and then it's simplifying to a rational function of type J over J, yeah, if I do that. The nice thing about this barycentric representation is that this interpolation conditions at that points at this index set will be already satisfied just by that ansatz here. And we only need to fix now the weights WL. We have only J plus 1 such weights, and we will do that in a good way in order to at least approximate all the other values that we have in fact to interpolate. So here I have given that again. So if one is computing that for the index set Sm plus 1, then we find out that our rational function at the point k squared is already equal to, say, ck tilde of f. Yeah, so that is a computation, just a simple one. So this is my ansatz. So these interpolation points have been done already. And now we need to fix the vector of weight coefficients in a way such that we approximate also nicely all the other data that we still have. And in order to do that, we try to minimize this sum here. This is, in fact, a linearization of the interpolation conditions. That happens often. That is often done in rational interpolation. So in fact, we wanted to have that ck tilde of f is equal to pj tilde of k squared over qj tilde of k squared. Yeah, so then we would have here the rational function. So, and we multiply with this part here and sum up over all the indices where we did not interpolate up to now, and just want to minimize in order to get here at least the error as small as possible. So, and if we do that, then it's everything, of course, only just depending on the W, because everything else has been fixed already in the rational function. And here comes in now our little modification. Therefore, it's called now modified AAA algorithm. This small modification that we have here for the weights ensures that we really get in the end a rational function of type j minus 1 over j. Yeah, so type j minus 1j instead of jj as it is in the usual algorithm. So this can be rewritten and means just that we take the W vector such that a certain matrix, a structured matrix that I call here L, Lj plus 1 times W has a smallest possible norm. Okay, and if you would not have that side condition, then it would be quite a simple thing to do. Namely, obviously, we can just take that weight vector to be the singular vector corresponding to the smallest singular value of L of Lj plus 1, and then we are done. So this is exactly what is done in the AAA algorithm. And this matrix here, it's coming from the structure of the polynomials that we have in the rational function. It looks this way. And this matrix has also a name. That is, so such a structure in matrices is called Löwner matrix. Yeah, we have exactly the k or the indices k here in the one index set and the L in the other index set. So the interpolation knots and the approximation knots, if you want to see that this way. So, and interestingly, what happens now in theory is the following. The error, usually the error is decaying if we go up with our j, and it will vanish the first time if j is equal to m. Yeah, so if we have the iteration step m, because then we can prove that this matrix indeed has a first time a kernel, which is not just the zero vector, a one-dimensional kernel, and the vector w that we get then in the kernel of Lm plus 1 also satisfies our side condition. So we are lucky to have it. And that is, of course, because of the structure that we started with. It has to be this way. Yeah, this is what I wanted to show you. This is a really nice algorithm. It works well also for larger index sets. And then in the end, we need to do a partial fraction decomposition of that rational function that we have found here. That can be done by a generalized eigenvalue problem, and that can be found also, for example, in the paper by Nakatsukasa et al., but also in other paper. It's well known. Yeah, so what we need to have to get such a partial fraction decomposition, we need the poles of the rational function, and that has been done already before. Okay, so we can summarize everything now in a theorem. And if we have a signal of that structure with our parameters m, gamma, j, aj, bj, as we said, in the suitable intervals, aj pairwise different and satisfying this periodic condition here, or non-periodic condition, then we can show, we can even show that 2m coefficients are enough if we take the classical way in rational interpolation. But this is really just a theoretical way. We practically we have to apply AAA algorithm. It will terminate. We can prove that after m steps, and will give us exactly the rational functions that we need to come up with our parameters. So, and that is working. I show you an example. This example is coming from Chui et al. In the paper from 2016. That is where they used it for EMD. And we have here, in fact, already also periodic frequencies that is here and there. And therefore, it's in fact not exactly suited for our working. So we look at the interval p equal to 4 and p equal to 8. And these are the plots. So this is what happens in the interval 0, 4. You see, it's not for periodic. And this is what happens in the interval 0, 8. You see it looks a little bit differently. And here are the errors. So just to show you that the reconstruction idea with the AAA algorithm with the help of Fourier coefficients is really working with quite small errors for the different parameters. And we take here the maximum error always with 20 Fourier coefficients or 40 Fourier coefficients. That is for the interval of length of 4. And here I have taken for comparison the matrix pencil method. But I have to say that, well, we have been forced to take a comparison with the Prony kind method. But in fact, it's like comparing, in Germany, we would say it's comparing Äpfel und Birnen. Yeah, it's comparing apples and pears. It's something different because we have completely different input values here. Here we have the Fourier coefficients and here we have function values. And for function values, we even need to pay attention about the step size a bit because we have a little bit larger frequency to recover. And I have fixed here for the matrix pencil method also the M, but in fact, it's not completely fair. I'd like to say something about the periodic frequencies that came up already in that case, namely what happens if we have that AJ is in the set 1 over p times integer. So then we lose the fractional structure as we had seen before. Of course, everything is still there, though all the parameters, gamma j, bj here, aj is now inside the n, if you want to see it this way, but only one Fourier coefficient, positive with positive index, is non-zero, and the fractional structure is lost. So what can we do in that case? Well, we can see that, of course, then if something like this happens, only this single Fourier coefficient is corrupted, yeah, by this form here, while all the others still stay with a rational structure. And that is also the idea to use here. We just take look at the f of t and take two different functions. The one which is still non-periodic, that is of that type as we had it before, where everything is working, yeah, where we have that the frequency satisfies this condition. And then we have the second function, phi2 of t, which is indeed a periodic function. It's p-periodic. And it's clear then that we need to have all these indices p times aj that come up here in the phi2 function that have to be in my gamma in the index set of the known Fourier coefficient. So otherwise I will not be able to recover the corresponding term in phi2 because it happens only in that one Fourier coefficient that it is non-zero. So this is what we need to assume here. But we also observe that all the other Fourier coefficients satisfy Cnf is equal to Cn of phi1. Yeah, that's true for any n in my index set. If I take out this Fourier coefficients that belong to phi2. And what happens here is if we just apply the algorithm that we have, then these values here, or the corresponding modified values, will appear as so-called unachievable points in the rational interpolation, and will just not be taken. And so in this way, we will be able to recover phi1, yeah, this non-periodic part. But if we have phi1, then of course we can simply find also phi2 in a post-processing step just by comparing the Fourier coefficients, and then we see what is missing, yeah, and then it's quite simple to find the phi2. And this is the idea. So this is what we have applied. We can generalize the model to extended exponential sums that has been done together with Nadia. And here we have, of course, many more parameters that we have to fix. I have put them all here. So starting with the m, the number of terms, then of course the degree of the polynomial coefficients and all the coefficients themselves. And it will work if we have just enough Fourier coefficients. We need at least 2 NP Fourier coefficients, where NP is here the number of, so we sum up over all the terms here. And here, this is the number of coefficients that happen in that polynomials. So this is at least that what we need. Yeah, better always if we have something more. I don't like to show you the theory. I'd like to show you a further example here. It's working really similarly. So we have here quite a simple example with only m equal to 2 terms. In the first term, we have here a polynomial coefficient of degree 4, and here we have a complex frequency. And in the second part, we have just a constant coefficient, and again here a complex frequency. So that means we have to recover the degrees with m, of course, then the degrees of the polynomial coefficients, so one time 4, 1 time 0, then the corresponding frequencies, the complex frequencies that we had here, and all the coefficients of my polynomial coefficients. And that is, of course, also what we get here, just an impression of the functions. This is the real part. So this is, of course, a complex signal. So therefore, I can only just show you, for example, the real or the imaginary part. Or here on that side, we have the absolute value on the interval 0, 8. This is what we will use also. The interval 0, 8, we will take 49 Fourier coefficients for recovery. And then our rational approximation procedure will provide us the poles Cj, which are related to our frequencies that we want to find this way. And you can see what happens here. We have obviously 2 different poles. This one is completely different from the other 5. And these here, these are close, but not the same. You see already in the second digit, they start to change a little bit. But we can look at these poles and we can judge ourselves if we would like to take it together as one pole, meaning then that we have a polynomial coefficient of the corresponding degree, or taking it separately and take constant coefficients, yeah, for in the model. Here we take everything together, take the average of that, and then it's interestingly even a very small error that we get here, and for the coefficients everything works out. So in the last part of my talk, I'd like to ask the following question. So we need to keep in mind, we have, of course, Prony's method, and that is different. It's different in particular because we use completely different input values. So usually in the Prony problem, we look at such exponential sums, for example, or if you put e to the lambda j to be zj, then it's looking like this. And we are given samples, equidistant samples, for example, fj this way, or if one can take it, of course, with other step size or starting somewhere else. Yeah, it's possible. We usually need, also in the numerical procedures, we need an upper bound for the number of terms m, and then we need enough values, of course, n has to be larger than or equal to L, larger than or equal to M here, and the number of terms is, or the number of values that we have here is 2n. And then the problem is usually to find these values, and that can be done, for example, numerically. Also, I will not show you now the classical Prony method again. We can We can do that by Esprit or the MPM method, matrix pencil. Both of them are very closely related. They are based on the observation that all these ZJ that we have here, in fact, are eigenvalues of a matrix pencil problem. Yeah, with a Z here. And the matrix pencil problem is built with Hankel matrices. So the Hankel matrices mean that we have here in the anti-diagonals always the same value. And these Hankel matrices are almost the same. You see here that here, what we have here as a second column is here exactly the first column and so on. So that's just one shift of column. And this Hankel matrix matrices can be simply given because we are given the Fj. Yeah, you just put it in. So it's a simple thing to do. So this is what is usually done. And now we see here, well, this is an eigenvalue problem. If you think back, we had also an eigenvalue problem with the Löwner matrix, namely also in the AAA algorithm, a different structure, not longer Hankel, but Löwner, but it is of course anyhow related. So what we asked, of course, is, can we replace, or we can ask us, say it the other way around. So how should we get Fourier coefficients of a signal? So there may be certain applications where it's working anyhow, but having just signal values is a nice thing. So in this way, Prony's method may be, or the Esprit and matrix pencil method may be preferred. So the question is, can we also do it just with function values? And that would mean, can we replace our Fourier coefficients with DFT coefficients? So because if we have given our sample values, then we could apply, of course, a discrete Fourier transform to get DFT coefficients. Does it still work? And I'd just like to give you a glimpse on that, that it's indeed the case. So if we assume again that we have such an exponential sum and we have given function values fk enough, yeah, 2n values, and we want to have these parameters, then we can do now the following. We assume, for simplicity in that moment, that zj to the 2n is not equal to 1. So this is what we need. So that means that the zj is not equal to a power of that 2n's root of unity. Then we take just the discrete Fourier transform of my given values. Here we have the given values. Here I take the discrete Fourier transform, which is that is just the definition here, yeah, of length 2n. Here these are my omegas, and now I put in the structure that I have. I know that FL is of this structure where T is equal to L. I put it in, change summation, take out the sum over J first, yeah, gamma J also, and I stay then with the sum over L here. But it looks simple. Yeah, so if this is not Zj times omega to the k is not equal to 1, and that is because I have assumed that, then I can rewrite that sum in this form, yeah, just using geometric series. So then we have it this way, and can pull out this omega to the minus k in order to get a little bit nicer the fraction. But we see we get again a fraction. So can we use that also? So I have put now the omega k to the left-hand side, and we get exactly this form. And now, again, indeed, we can just take a rational function of that type here, take the aj just the same way as we have it here inside. And then we see that this rational function that we have here, exactly, if we put z here to be omega to the minus k, then this rational function exactly satisfies r at these points. Yeah, we are on the unit circle. Yeah, the rational function at the unit circle is equal to these values for k from 0 to 2n minus 1. So we are back to rational interpolation, and that is, of course, what we can do. So I just give you the pseudocode here, and we get here then, if we are given equidistant sampling values f of that type, then we can, in a first step, just apply the discrete, the DFT to get f hat. Then we take the we find the rational function R of Z of that type such that all interpolation conditions are satisfied. I've written it this way now. It's again with the AAA algorithm. Then we take the partial fraction decomposition and find our parameters. So it's working. It's working the same way. And that is my last example here. If we consider, for example, the sum with 13 terms, ZJ, these are my knots. I have put here, I didn't give you the ZJ, but I put it here on the circle, on the unit disk. These are my gammas. They are very simple here always, but the knots, you can see it here. They are, some of them are really directly on the unit circle. Some are inside. These are 2. This is a small cluster. And here are 2, and here we have even 3. And here one is, and that is a bad example in that way, one knot is really very close to another one, namely the distance is only 1/1000. It's very, very close. And then we get this errors. And you see here our Aspira algorithm works really well also compared to matrix pencil, where I have to say that in the matrix pencil method, we have taken the upper bound that we have to take anyhow as m+10. And if one is playing here a little bit differently, then matrix pencil sometimes is also better. So I have to say that. But interesting to us, we look at the Hankel matrix that happens that we have to use for the matrix pencil method, and to the Löwner matrix that comes up in the Aspira matrix, in the Aspira method, then we see that the singular value that is not the kernel value, but the next one, they are quite different. So it seems that we really are able to stabilize here a little bit by our algorithm. And that is what I also want to tell you in the summary. So I have shown you here a new numerical method to recover all the parameters of such an exponential sum in particular, but we can do that also for extended exponential sums. And it's working just with a finite set of Fourier coefficients. And what we use, and which is important, is this adaptive rational interpolation algorithm by Nakatsukasa et al. The idea can be also applied to DFT coefficients instead of Fourier coefficients, which is interesting if we just only have function values given and not Fourier coefficients. And the algorithm seems to be quite stable. So in particular, so at least as good as MPM, and in particular, it's working well also for noisy data. I didn't show you that, but we will do that in the paper. So here are the papers. One has just appeared in the new journal here, Assembling Theory, Signal Processing and Data Analysis. The second one about the extended exponential sums is an archive from March, and the Aspira idea here, the idea using really function values will come up. So we will try to be quick. Thank you.
Yes, thanks a lot for the nice presentation. Are there questions? Please feel free to just unmute yourself.
Can you please give us a glimpse of what are your results in the noisy setup that you were just like
yes.
ended upon?
In the, well, we in the problem in our case. So in fact, I didn't tell you everything because the paper is not done here. So the one, I hope that we have a first version, maybe in archive, maybe next week or in 10 days. Yeah, but
for me, I'm just interested if you could announce the result, perhaps.
Yes, the idea is, I think, so that is my heuristic idea. The going with the data to the Fourier domain, so to the DFT data. Anyhow, maybe there is already a certain smoothing process or something. It's really working in our case for the Aspira. In fact, it does not work for the Aspira algorithm that I have given to you here, but but slightly changed. This, therefore, it's called Expira 1. There will be an Expira 2, where we use this idea of the AAA algorithm only for this preconditioning. I think what happens in the AAA algorithm here for finding this good interpolation points in order to always to reduce the interpolation error, this adaptive selection is like a preconditioning process for the corresponding matrices, and that is the reason why it's working further better than the usual algorithms, also for the noisy case.